We're going to continue talking about acid-base chemistry. So this week we'll finish out titrations, which are really just a summary of everything that you kind of learn along the way. So, right, we'll do buffers, and then titrations are kind of like, it takes buffers and all the stuff we did with weak acids and strong acids and neutralization reactions and stuff like that and sort of combines it into one long problem. So if you've been keeping up, it won't be that bad. If not, you kind of have a good amount of catching up to do at this point. So we started with last class, we left off just kind of looking at this problem, which was just trying to figure out what the pH change is. If I take 0.01 moles of nitric acid and I add it to a 5 molar solution of acetic acid, what does the pH come out to be? We sort of went through this calculation here where we said, okay, we've got nitric acid, that dissociates and gives you 0.01 molar H plus, and then we want to go ahead and solve for what our proton concentration is in this equilibrium reaction with acetic acid. So we plug in the value for nitric acid and what we started with acetic acid, and we come out with some algebraic expression down here. And then we go ahead and we solve that in the standard way that we solve these things. We tried some approximation and it didn't work. And ultimately, what we realized was we could approximate that 5 minus x is approximately 5, but 0.01 plus x is, you can't approximate that as 0.01. And so I think we left off right here, and I just went ahead and solved this. All you have to do, once you make that simplification, all you have to do is then turn this into something that you can plug into the quadratic formula, which is just right here, which I just used to solve our online, and you end up with x equal to 0.0057. And then so you can take that and come back and say, okay, well, what I wanted ultimately was to figure out the pH. So I've got this H plus over here, which is equal to 0.01 plus x. And that's what I rewrite that down here. And so 0.01 plus x gives me 0.0157. And so finally I can get my pH, which is equal to 1.8. So you can see these problems, they get pretty long. Computationally, there's kind of a lot of stuff to keep track of. So they take a lot of practice. Okay, so the nice thing is, so in this problem, we're not dealing with a buffer. All we have here is an acid. In order to have a buffer, you have to have an acid and its conjugate base pair. We can take a look at what happens when you have that situation. So we can say, let's see, so what does the pH change? So we could say, let's just look at several different solutions here. So we're going to look at the same kind of system where we're dealing with acetic acid. We're going to say, first we'll say, what is the pH of a solution of 5 molar acetic acid and 5 molar sodium acetate. Okay, so spacebar is jammed up. Oh, on my computer. That's my shitty ass MacBook Pro keyboard. I think that fixed it. Oh, your spacebar is jammed up. Oh. My spacebar on my MacBook Pro is jammed up. The I got the generation of MacBook Pro where like the space, they tried to make a new keyboard and it was complete junk. Like a tiny particle will cracking me up. All right. All right. What is the pH of a solution of a 5 molar acetic acid and 5 molar sodium acetate? Yeah. So the thing to recognize here is that you have the acid, but we also have its conjugate base. Let me mark off. So this is really the conjugate base here. This part that I'm outlining in yellow is just the counter-cation. So that could be a lot of different things. So, you know, the sodium could be potassium. You could have potassium acetate. You could have really any kind of cation out here is going to be the same thing. So if you, there's a ton of work with recognizing acid-base salts. If that's kind of confusing, this concept of like, what the hell is the sodium doing there? Make sure you go back and kind of look over those. You don't want to get tripped up on that on an exam. All right, so yeah, so we've got this problem is what is the pH of this? And so we recognize that there's an acid-base conjugate pair. And so that cues us in that we have a buffer. And if we have a buffer, we can skip a lot of calculation here. So normally when we set this equation up, which is, this is an acceptable way to do it, you would write out your reaction. And then we would plug in values here. Say, okay, we got 5 of that, 5 of that. We don't know how much of this, minus x, plus x, et cetera, et cetera. But because this is a buffer, we can use the Henderson-Hasselbach equation, which is that the pH is equal to the pKa plus the log of A minus, which is the conjugate base, over the acid. And this allows us to rapidly calculate this. So we can, so Ka for this is equal to 1.8 times 10 to the minus fifth. So the pH is equal to the negative log of 1.8 times 10 to the minus fifth plus the log of A minus, which is what's outlined in green up there, divided by HA, which I've highlighted in pink. And so those are both 5 molar, which is very convenient. So that means that our pH is equal to pKa. So you can see how the Henderson-Hasselbach equation, even though it is an approximation, it's extremely, it just makes things a lot easier, right? So when is this valid? It's valid when you have an acid-base conjugate pair. If you don't have that and you use the Henderson-Hasselbach equation, you risk making an approximation that is incorrect. This is 1.8 times 10 to the minus fifth, just because that's the value of the Ka. So the pKa is the negative log of, yeah, that's just a given in the problem. Yeah, no worries. I didn't take the negative log of the pKa. I took the negative log of the Ka. If you put a p in front of anything, that just means take the negative log of it. So like Ka is equal to 1.8 times 10 to the minus fifth. pKa is just going to be equal to the negative log of Ka. So negative log, well, yeah. So be anything is negative log transform. Okay, so why are buffers important? We can look at what happens to this solution if we start adding in acid. So buffers resist pH change. That's their whole deal. So if I take this and I add in, let's say we add in, so let's look at two scenarios. What happens if we add 0.01 moles of HCl to So we're going to add that to our solution of 5 molar acetic acid that also contains 5 molar acetate. Okay, so how do we do this? So we start out, so identify, I'm just trying to cue your brain in, that we have this acid-base conjugate pair here. So we know we're working with a buffer. And so if you're trying to understand how the pH changes for a buffer solution, we would start by, but we're adding in something. So here we're adding in this strong acid. So if you're adding strong acid or you're adding strong base to a buffer solution, you're dealing with a neutralization reaction. So step one is write out the neutralization reaction for this. So we're adding in acid. So what is the acid going to react with here? It's going to react with our conjugate base. And so what that's going to do is it's just going to consume a little tiny amount of our conjugate base. So at the beginning of this, right, we have 0.01 moles of HCl and 5 molar acetic acetate, excuse me. And then at the end of this, we'll have 5 4.99 of that. And we'll have picked up this tiny amount of acetic acid. Yeah, Ka is the same. Ka is set for acetic acid. It's always the same unless you change the temperature. For rice tables, using moles or molarity, it doesn't really matter which one you use. You just want to make sure that you keep track of the volume at the end of the problem. So you can work in moles for the whole problem and then back out. Well, is that true? Generally, you want to work in molarity, I guess, because Ka is tied to the concentration. So try to stick with molarity. Ka is a constant, yes. Ka is the equilibrium constant, at constant temperature at least. Okay, so anyway, the result that we're looking at here, though, is that the pH is equal to, so because we know we have a buffer, we can avoid a bunch of laborious rice table type calculations and just plug in our new values for A minus and HA. So in the original problem, A minus and HA were exactly equal. So you had log of 1, so that cancels that to 0. Here it's almost that. So the pH is going to be equal to the pKa, which is negative log of Ka, which we know from our last problem is 4.74, plus the log of a minus. And so we take this value here and plug it in. Divided by 5.01. So all we've done here is we've said (0.01) is that's in molar. All we've done here is we've looked at, we said, okay, we have a buffer that's 5 molar acetic acid and 5 molar acetate. If I add in a little bit of acid, what's going to happen is that's going to consume a little bit of the base. And I just need to keep track of what that is. The amount of base it's going to consume is exactly the amount of strong acid that I've added. So I start out with 5 molar acetic acid. I start out with 5 molar acetate, which I've highlighted in green here, and I end up subtracting out the 0.01. So I end up with 4.99 of that. The amount of acetate that I lost, because it's a conjugate acid-base pair, ends up becoming the acid over here, which I track in this table over here. So I say, okay, well, I lose 0.01 moles of acetate, and I gain 0.01 moles of acetic acid. And then I just take these numbers. These are my new values for acetic acid and acetate. So it's how these relative concentrations have changed once I've added the acid. And I just plug it into the Henderson-Hasselbach equation. What I end up with is something that's going to be very close to 4.74. Yeah, so log of 4.74, I'm sorry, 4.99 divided by 5.01 ends up being this really small number, which is what you expect because it's very close to 1, and we know that log of 1 is 0. And so the pH change that we see is .73. I'm going to write it out even. Yeah, 4.738. So we'll keep it. So what we see is that the pH does change, but it just changes a teeny tiny amount. And that's kind of the whole thing behind buffers, is that they maintain the pH close to what the starting pH is. It buffers against the addition. The term means it is used because it buffers against the addition of acid or base. It like buffers the pH and keeps it near the initial pH. Okay, let's see if we get some questions. If you have a reaction where you just plug in acid, some kind of neutral salt. I'm not ask about the specific situation with an acid and sodium chloride in office hours or something. But yeah, if you, yeah, acid and a neutral salt, sorry. So neutral salts just don't react with anything. You can think of it in terms of pH as having no effect on the pH. So if you had sodium chloride or something, just assume it has no effect on the pH. Okay. Let's look at this result though. So we've got this situation where we see that the solution is very, very resistant to pH changes. So we know that the pH of, if we just take the 5 molar solution of acetic acid and an acetate, what we end up seeing is that we have a pH of 4.74. If I take that solution and then I go ahead and add some amount of acid to it, 0.01 moles of HCl, what I see is that my pH doesn't really change for that solution. I still have a pH that's about 4.74. If I had a different concentration though, like, so this is sort of an ideal case of how you would prepare a buffer. If I take this though and I say, what happens? So we're going to change the buffer a little bit. What happens if we add 0.01 moles of HCl to a solution of 5 molar acetic acid, and 0.05 molar acetate. All right, so I still have an acid and I still have its conjugate base down here. What's changed is now the conjugate base concentration is 0.05 molar versus the conjugate acid, which is 5 molar. But it's still a buffer because I have both present. So for my buffer, HA is going to be equal to CH3COH, which is going to be equal to 5.0 molar. And then A minus is going to be equal to which is going to be equal to there we go. So then we just want to take and we want to do kind of the same thing that we did before. So this is where we start. This is sort of the starting buffer concentration. So we could look at what our pH is initially. So our pH is going to be equal to the pKa plus the log of A minus 0.05 divided by 5. So it's going to be equal to 4.74 plus -2. That's going to equal 2.74. So we're starting out at a more acidic pH here. We're starting out at a more acidic pH here. Oh, no. Let's actually change this a little bit. I'm sorry, guys. This is a better lesson. There we go. Sorry about that. All right, let's look at this problem instead. So instead of saying what happens if we have 5 molar acetic acid and 0.05 molar acetate, now all I've done is, yeah, this is happening in 1 liter. So up here, we have 5 molar and 5 molar. So down here, we've just changed this so where the relative concentrations stay the same. relative concentrations stay the same, but we've decreased the absolute concentration. So before we had 5 molar, but now we have 0.05 molar. And so this is a more interesting result to look at. So here we see that our pH is still 4.74 because this term becomes 0. But what we can look at is we can see what happens when we actually add in our acid. So if I add in acid, we look at the neutralization reaction to start. Or let's say you just take your base. So that's A minus. So the reason I know to take the base is because I'm adding an acid. That's where the reaction, naturally the acid's going to react with the base. So I say that I take A minus and I'd say, okay, I've got 0.05 molar of that. So I subtract out the 0.01 molar HCl that forms, which gives me 0.04 molar A minus. And then any A minus that I lose is going to be picked up by the acid. So the HA concentration now goes from 0.05 molar plus 0.01 molar. So that's now 0.06 molar. So that sort of takes care of the neutralization reaction. So this is our new buffer concentrations. After neutralization. And then we just plug those values back into the Henderson-Hasselbach equation, and we see that the pH is equal to 4.74 plus the log of 0.04 over 0.06. And so this ends up being 4.74 minus 0.176. No, 0.176, not 0.0, 0.176. And then we end up with 4.74. So our pH ends up being 4.56. And so we can compare what's happened here. So initially, let's see, I'm going to write this out. So let's say in one solution, I know how to do it. Let's say we have a buffer. A little more clearly. So we have a buffer made from this, where this is equal to 5 molar, and this is equal to 5 molar, and we also have a buffer so a different solution. So we'll call this like solution 1. This is solution 2. So both of these start out with a pH of equal to 4.74. But what we see is that if we add 0.01 molar acid to it, that this pH goes from 4.74 to pH of 4.56 on addition of 0.1 molar HCl, whereas this one, which just goes to a pH equal to 4.7, I think it's like 4.738, addition of 0.1 molar HCl. And so the result here just shows us that for a buffer, the larger the concentration of the acid-base conjugate pair, the more resistant the solution is going to be to pH change. So if I start out with 5 molar acetate to acetic acid, what I see is that I can add some acid in and I see very little pH change here. 4.74 to 4.738 would be difficult to even detect using like a traditional pH meter or whatever. Whereas if I come down here and I look at this other situation where now I've lowered these concentrations 0.05 molar, my starting pH is still the same, but now when I add in a 0.01 molar acid, I can see that pH change, not super dramatically, but at least it's detectable at this point, 4.74 to 4.56, where it's not just like a rounding error in the calculation, right? So larger buffer concentrations give you larger resistance to pH change. That's really the only lesson that comes out of that. You can see one of the nice things is that working with the Henderson-Hasselbach equations allows you to go kind of really quickly with these calculations. Like this is a much easier calculation than dealing with a Rice table. But you'll hear people refer to something called the buffer capacity. I have to look at how we've asked this previously, but buffer capacity is really, this is like, it's the ability of I guess I'd say it's like a measure how resistant is a buffer to pH change. And it changes for different, what am I trying to say here? It depends, it's situational, as far as exactly how you calculate the buffer capacity, because it depends on what kind of pH change you need to resist. But like a good, I guess a metric for how to kind of look at it is, it's kind of equal to, it's approximately equal to like whatever the concentration is of one of your components in solution is. So the ability of solution 2, for example, to resist pH changes is going to be, like if I add acid, it's going to resist pH changes up to about 0.05 molar acetate, and then the pH is going to start to vary wildly because you'll have consumed everything, all of the acetate in solution. Whereas if we look at this top one right here, the buffer capacity for that one, if you're adding acid, is going to be closer to 5 molar. You'd be able to have 5 molar acid. And then after you add that, your pH will start to change really rapidly. So your buffer capacity is sort of the a measure of like how long you can continue to add acid until you sort of break the sort of buffer system. I guess a way to look at it is like if we consider a buffer as being an acid-base conjugate pair, the buffer will resist changes in pH, because if I add acid, A minus is consumed. If we add base, HA is consumed. And so that's sort of where the resistance to the pH change happens. But if we add, you'll exceed the buffer capacity if all of HA, or say all of A minus when all of A minus or HA is consumed. So for example, in the last problem, if we looked at what is the pH of a solution of, let's say, 0.05 molar acetic acid and 0.05 molar acetate, 1 liter. After the addition of 0.1 moles Okay, so note here, I still have an acid-base pair. I'm looking at this buffer, same buffer system. I've got my base over here. I can put in the sodium if you want. And now I've added acid, but I've added a lot of acid. And so when I say a lot, I'm saying that's a lot relative to the concentration of the buffer. So you can see that the amount of acid that I'm adding, 0.1, exceeds the amount of buffer that I'm starting with, which is 0.05. So in our neutralization reaction then, if we start out with our initial concentrations of acetic acid is equal to 0.05. In our initial concentration of sodium acetate is also 0.05. At the end of the neutralization reaction, the final concentration is going to be 0.05 plus the 0.1 moles of HCl that I added. So it's going to be 0.15 molar. And then how much base are we going to have left over? That's just going to be equal to 0. And this just falls right out of the neutralization reaction, where we're looking at the situation. You can write out the reactions if you want. That's where I would start, because I'm a chemist. But it's sort of however you want to keep track of things bookkeeping wise. I've added in 0.1 moles of this. And so I have to look at the neutralization reaction that happens there. If I started out with 0.05 of this, all of that is going to be consumed by the H plus. Oops. So if my initial, I'm just rewriting this to make it more clear, or I guess elaborate on it. I don't know if necessarily makes it more clear. At the end of the reaction, I'm still going to have 0.05 of this. I'm going to have 0 of this, but I will have formed 0.05 of that. That's actually the right way to look at this.
Didn't we already have an initial of it? So
Yeah.
it'd be like 0.1.
Yeah. Okay, so yeah, so then our final concentrations here end up being 0.05 and 0.1 of this. So what I've done here, though, wait. I see what you're saying. Yeah. So our initial concentration was 0.1 of this. I started out with 0.05 of the acetate and 0.05 of the acetic acid, but my proton concentration exceeds the amount of base that I have there. So at the end of this reaction, I end up with no acetate. I end up with some H plus, a strong acid left over, and I formed 0.1 molar acetic acid. And so if I want to calculate the pH now, I no longer have a buffer. Since this is equal to 0 and this is equal to 0, this is equal to 0.1, right? I have my conjugate acid is present in solution, but its conjugate base is not, because this is equal to 0. So when the conjugate base, if the concentration of the conjugate acid or base is 0, then it's not really present. And then I also have some strong acid lying around. That's equal to 0.05. And so now when I calculate the pH, I can't use the Henderson-Hasselbach equation. I'm not sure how to spell this guy's name. I like that. Because we don't have a buffer. So now we have to treat it like any other acid-base problem that we've learned before, where we'd say the problem is now, you would say, like, what is the pH of a 0.1 molar solution of acetic acid and a 0.05? That's also 0.05 molar in H plus. And more than likely, the pH is just going to be equal to the negative log of the H plus concentration. So I guess I'll write it out. Since we have a strong acid, weak acid, pH can by ignoring contributions from the weak acid. So we'd say our pH is going to be equal to the negative log of 0.05. So just plugging in this value from up here, and I'm ignoring the contributions from acetic acid, which is going to be about 1.3. So you can go through. You can go through and calculate the contribution of acetic acid if you wanted to, but it's going to be small and probably insignificant. Okay.
What would happen like if we had like a strong acid and like a weak base that made up our buffer? Where is
Strong
that?
acid and a weak base. So you can't, yeah. So the question, which is a good one, is like what if you had, so like if you tried to make a buffer from HCl, so you can't make buffers from strong acids and bases, I guess is what I'd say. So like if you had HCl and you tried to make a buffer from that, that would say HA would just be equal to literally H plus, and then A minus would be equal to chloride. And this just doesn't end up. So I guess what I'm trying to say, what I'm not doing a good job at, is that in order for the buffer, I'll just put it succinctly, buffers can't be made from strong acids and bases. Or I should say more precisely, strong acid-base conjugate pairs. So you wouldn't be able to make a buffer from, say, like HCl and Cl minus, or HNO3 and NO3 minus. Not buffers. They absolutely have to be weak acid-base pairs. Yeah, because they dissociate too well. In order for the pH to be, for it to buffer against pH changes, the conjugate base actually has to react. So if you have something like this, there's not really an equilibrium there. So if I add, let's say the addition of acid doesn't result in a reaction with chloride. Somebody asked a question about this earlier. Addition of acid doesn't result in a reaction with chloride. So if I have if I have a 0.01 molar solution of HCl, that's also 0.01 molar solution of Cl minus. If we add in another 0.01 moles of, and let's say this is in 1 liter, if I add 0.01 moles of HCl, what I end up with is a 0.02 molar solution. Or let me give you a different acid there. Let's say nitric acid. What I end up with is a 0.02 molar solution of H plus and a 0.01 molar solution of Cl minus. The issue is that, so in a normal buffer problem, right, when we add in acid, it reacts with the conjugate base. But if your conjugate base is so weak, like Cl minus, that it can't react, when I add in acid, nothing happens, right? The acid concentration just increases. It doesn't actually get consumed by the conjugate base. So that's why strong acids and bases don't form buffers. Buffers require like an acid and a base that's capable of reacting. That's how it actually, that's how the buffering actually works. It's like here, it's like if I look at, where would I have the equilibrium drawn out? All right, nowhere. If I look at an actual buffer solution, we'll end on this note. The reason it buffers, 1 molar of this and 1 molar of that, is if I add acid, it can react with a CH3CO minus. If I add base, it can react with a CH3COH. The problem with the HCl is it can only go in one direction. So if I add, let's say I start out with 1 molar of each of these. If I add acid, it can't react with that because the reaction doesn't go in this direction, right? It won't go backwards. And so it's not resistant to pH change in that direction, so it's not really a buffer. What about the strong acid base with excess weak acid base? So if you have so in the question, somebody asked, what about a strong acid base pair with excess weak acid base? Then you're still in the buffer. Then you just have a buffer. It's when you get to excess strong acid base that you're outside of the buffer range. So then you have to treat it like a different type of acid base problem. But as long as you have some of the weak acid and base present, but simultaneously, you have a buffer solution, and you can use the Henderson-Hasselbach equation. So yeah, so this is how buffers work. We will look at titrations in next class. I'm trying to think. Well, we might talk a little bit more about buffers from a practical perspective. Like if you want to make a buffer that's resistant to pH change, what's the right buffer to choose, etc. But then we'll quickly switch over to titrations, and that's at least where we'll finish the acid-base stuff. Yeah, we'll look at indicators as well, but that's pretty straightforward. Okay, all right. Let me give my. No, we'll just talk about titrations next class. So if you're like to prep for the titration stuff, just practice everything up until now is the best thing you can do, because it shouldn't feel completely new. Like you shouldn't feel completely caught off guard by titrations. A lot of it should make sense, and then there's some additional lessons to build on it. But so just practice the stuff that we've done. Yeah, exam 2 is next Wednesday, so we're like 9 or 10 days out. All right, I'll see you guys in a minute. I'll try to put it up immediately afterward. What keeps happening with the damn YouTube videos is that Zoom has to convert it to MP4, and then I have to upload it, and then sometimes that takes a while, and then I forget because I just get distracted with something else. So I try to get them up immediately after class. So if it's not up immediately after class, just shoot me an email or something. That means I just got distracted and forgot. But thank you for understanding. Okay, give me a second. Let me get my voice rested up and drink some water. right. Do you guys have specific questions? Let's see. Separate problem. I made a couple of problem solving videos and I forgot to turn the damn volume on the mic, but they're just they're on the YouTube channel under like Unit 2 problem solving. I don't know how useful they are without the damn audio. I hate when that happens. But yeah, I've kind of haven't done a great job of making problem solving videos. The second half of class for Monday, Wednesday is, mostly just solving problems. So they're just not very like produced in the way that the other ones are. Let's see. Problem 16 on the homework. Are you looking for which homework? On the homework, like assigned homework, whatever, homework 4 or 5? Wait. Just tell me which homework about that. I think that would be, okay, that would be 5 then. Yeah, so we got 16, 17, and 30, or whatever the last problem is, 16, 17, and 20. I'll just go over. Okay. What would the final pH of a 0.01 mole what would the final pH be? I see I'm missing some words there. If 0.01 mole sodium hydroxide were added to, oh wait, I'm crossed between problems, hold on. 16. Yeah. Would be the final pH if 0.01 mole sodium hydroxide were added to 100 milliliters of buffer containing 0.6 molar formic acid and 0.3 molar sodium formate. It tells us that Ka is equal to 1.8 times 10 to the minus 4. All right, so this is basically the same problems that we just worked, or similar to the problem that we just worked in class. We know we have a buffer because, well, they're telling us, but also because you can identify the acid and its conjugate base pair, and that's the concentration of A minus, and that's the concentration of HA. So for buffer, you want to identify what HA and A minus is. So HA is going to be equal to this, which is equal to 0.6, and A minus is going to be sodium acetate, which is equal to 0.3 molar. So this is a little bit different in that you have a different starting concentration of acid and base. It's not exactly equal. This is our initial buffer solution. And now we've got 100 milliliters of buffer. Yeah, there's some concentration stuff to deal with. So we have 100 milliliters. Oh, okay, but you're adding, okay, so yeah, you're adding a solid, so you don't have to worry about dilution that much. Let's see. How do we want to deal with this? I think I like to back everything out into moles and then go back into I don't think it matters in this problem, but I guess it's quicker to do it the other way. So you can figure out it's like how much base. Well, now let's back everything out in the moles. So you're starting out with 0.06 moles of HCOH. 0.03 moles sodium formate. All right, and then we're adding in 0.01 moles of sodium hydroxide. So this is base. So the neutralization reaction is naturally going to happen with whatever the acid is. So if you have a buffer, you're adding base to it, it's going to react with the acid component of the conjugate acid base pair. Okay, so initially we have 0.06 of this and 0.3 of this. Let's say we have 0 of that. Well, I forget, I'm trying to be consistent in how I work these. Yeah, we could rewrite this out, right? So 0.01 moles of this, water we don't care about. At the finish of that reaction, we're going to have 0.05 moles of formic acid, because that's going to react completely with the sodium hydroxide. We're going to have none of the sodium hydroxide left over. And then we're going to form formate over here. So we'll have 0.04 and again, water we don't care about. So then this is all in moles. It's just easier for me to think in moles than in concentration, so that's why I back it out into moles. And now I just want to put everything back into concentrations. So now I say, okay, I want to put this, my concentration now that the like post adding 0.01 moles of sodium hydroxide is just going to be equal to the amount of formic acid that I have. divided by the volume. So I have 0.5 molar of that. This is HA in the Henderson-Hasselbach equation. And then A minus, which is going to be equal to sodium formate concentration, 0.04 mole. And so our pH here is going to be equal to the pKa plus the log of A minus divided by HA. That's going to be negative log of whatever the K value was that was given to us, which is 1.8 times 10 to the minus. It's interesting. 10 to the minus 4. Plus the log of 0.4 divided by 0.5. So we end up with pH equal to 3.64. Let's see if that's in the answers. Yeah, correct answer is 3.65. So I don't know, some sort of rounding error on my part, maybe. But that's how you work this. So you do the neutralization reaction, and then you recognize. So somebody at the end of class was asking what happens when you have excess weak acid, weak base, and these types of things. So here we're adding in strong base, but we have an excess of the weak acid base conjugate pair is one way to think about this. And so if you have an excess of the weak acid base conjugate pair, so you don't consume it all, then you're dealing with a buffer. So you just use the buffer equation. If you use so much sodium hydroxide that you exceed this concentration, and then you have excess of strong base, then you just deal with the strong base. So it's sort of situational in terms of how to work these problems. Let's see, so that was 16. 17. All right, here we have a buffer. Was prepared by mixing 0.2 moles of ammonia. And they give us the Kb here. And 0.2 moles of ammonium chloride. That's going to form an aqueous solution. With total volume of 500 milliliters. 250 milliliters of the buffer. It's a long question. Was added to 50 milliliters of 1.0 molar HCl. What is pH of this second solution. Okay, now that we're done writing that short novel, let's reassess what this thing is. All right, so it's telling us that we have a buffer, we've got 500 mils of it, and it's saying we take 250 mils of that buffer and we add it to 50 mils of HCl. And they're asking what's the final pH here. So things that stand out to me in this problem immediately is you've got an acid and you have its conjugate base. So you know you have a buffer. They also tell you it's a buffer. But the other thing that stands out here is that the concentrations of these things are well, let me think about it. 50 milliliters of 1 molar HCl, but you've got 250 milliliters of the buffer. Yeah. I'm thinking in terms of like how well can this solution buffer against 1 molar HCl? But since they're dealing with concentrations here, which make it a little bit annoying, we have to take that into account. So again, I back everything out into moles first. So start out. So when you write out your buffer, when you write out your chemical equation for your buffer, if you're using the Henderson-Hasselbach equation as it's given to you, I'm going to drop the chloride. If you're using the Henderson-Hasselbach equation as it's given, it's written in terms of the pKa. So you want to write the reaction for the acid to be on the reactant so that you can use Ka. So they give you Kb up here. I would calculate Ka from that. Otherwise, you can use there is a way to write the Henderson-Hasselbach equation in terms of Kb, but it's a pain in the ass. To me, it just makes sense to just use one equation. Or, yeah, this is fine. Let's see, so we know that the Ka is going to be equal to the Kw divided by the Kb. So this is equal to 5.5. So minus 10. So pretty small equilibrium value for that. Okay. Yeah, what's the easiest way to do this? So I would think about it in terms of another way of phrasing this question would be to say, like the way that we've kind of talked about it in class, it would be the same as saying, what happens if you add 50 milliliters of 1 molar HCl to a 250 milliliter buffered solution of ammonia and ammonium chloride? So in my mind, the way I'm thinking of it is like I'm adding, because the order of addition doesn't matter here. These things are going to come to equilibrium, but it's the same as adding 50 milliliters of 1 molar HCl to 250 milliliters of a buffer solution of ammonia and ammonium chloride. So you want to be careful here. You want to calculate the concentration of your buffer solution. So our ammonia concentration is 0.2 moles. But I have that in 0.5 liters. And then I think the other one is also, yeah, they're both 0.2 moles. I don't know. I guess there's a lot of different ways to think about this. Like when to go between moles and concentration is kind of a personal decision. But you could rephrase the question as it's like you're adding 50 milliliters of 1 molar HCl to 200 milliliters of a buffer solution composed of 0.4 molar NH3 and 0.4 molar NH4 plus. Yeah, the exams are always about the same amount of problems. For the acid-base one, though, it's not going to be, we take into consideration the fact that some of these problems are pretty intense calculations, so it'll be, should be able to finish it within the time allotted. Okay, but so yeah, so we're adding 50 milliliters of 1 molar HCl to 200 milliliters of a buffer solution. And so now we can just think about it like a normal neutralization reaction. So if I'm adding acid to my buffer solution, I want to be thinking about it in terms of its reaction with the base. Okay, so here again, probably makes sense to back things out into moles. So 50 milliliters of 1 molar HCl. If we want to know how much that is in terms of moles, we want to, it's moles per liter. So yeah, you just want to multiply those numbers. It's going to be 0.05 moles of this, and you have 250 millis. Yeah, especially here because you're dealing with some dilution effects and stuff. It definitely makes sense to back out in terms of moles. But here we have 250 mils of that, and so we want to multiply that times 0.4 molar. So 0.4 times 0.25 gives us 0.1. So these numbers are calculated from the concentrations in the volumes. So that's at the start of this neutralization reaction. When this thing's all said and done, we know that we are going to still have some ammonia left over. We're going to have no acid. We're going to have 0 of that. But we're still going to have some ammonia left over. We're going to have 0.05 of that. And we're going to have formed 0.05 moles of this. So now we can calculate our new concentration. So this is the situation where you've added acid to the buffer, but you haven't added so much acid that you've exceeded the buffer concentration. So I should write out over here, we're starting with 0.1 moles of this as well. But you haven't exceeded the concentration of buffer. So like the situation where you've exceeded it would mean that you have greater than, like if you're adding acid, you would have greater than 0.1 moles of acid. And so at the end of the reaction, you have no ammonia left over. Now you're outside of the buffer range, but so we're still in the buffer capacity here. And so now we just want to back everything back into concentrations. So say, okay, the ammonia concentration is just going to be equal to the number of moles of ammonia that we have. And we're going to use the total concentration up here. So like at the end of this, we're going to have 300 milliliters of solution. So we have 0.3 liters. So our concentration is 0.16 or 6.17 molar. And our concentration of ammonium I messed up. I need to add the amount here. This bookkeeping method I use is not perfect. But we have 0.15 moles. That's also divided by 0.3 liters. So now I have 0.5 molar. So because I have still have an acid-base conjugate pair, I can just use this equation. So the A minus over HA doesn't work super well here because it's not really A minus. This thing's not charged. Ammonia is neutral, but it's still the base over the acid. And so I converted things to the Ka to make it easier at this point. So we know the Ka is equal to 5.5 times 10 to the minus 10th. And so now we can just calculate it out. The pH is going to be equal to the negative log of 5.5 times 10 to the minus 10 plus the log of the ammonia concentration, which is 0.17, divided by 0.5. So your pH ends up equaling 8.77. Yeah, I mean, I'm always off by 0.01. Correct answer is 8.78. Yeah, it's a long problem, but it ends up just being a neutralization and a buffer. A neutralization. It just ends up being a buffer problem where you do a neutralization reaction, then just calculate your new buffer concentration. So, yeah, I'll do 20 next. So there's several difficult parts in the acid-base chemistry thing. I'm not even sure how to outline exactly what the most difficult part is, but ultimately in these problems, what you're trying to figure out is after you work through all of the acid-base reactions that happen, like all the strong acid, strong base type reactions that happen, so the neutralization reactions, you want to look at what's still present in solution, and that dictates how you solve the problem. So after the neutralization reactions are done, you consider all the different components that are present in solution, and that's how you kind of figure out what to do. So the neutralization is the first step, and then after you're done that, they're sort of like, what situation am I in? In this situation, after all of the neutralization reactions take place, I recognize that I still have a buffer, and so I just use the buffer equation, which is this Henderson-Hasselbach deal.
Why couldn't we just straight divide 0.2 moles by 250 milliliters in the beginning, since to get the molarity?
You could do that. It just depends on how you want to think about it. Let's see. Yeah, you could say, so 0.2 divided by 500 mils will give you the molarity of the buffer solution. Ultimately, it makes sense to me to think in terms of moles, just because it leaves volume out.
But
and then
you couldn't divide 0.2 by 250 milliliters?
No, because I see, I misunderstood your question. No, because the 0.2 moles is divided. So you're dissolving 0.2 moles into 500 milliliters, and that's going to give you one concentration. If you were to dissolve the 0.2 moles into 250 milliliter, that would be a different concentration, right? It's moles per liter is the definition of molarity. Does that make sense?
Yeah.
If you divide by 250, you end up with double the concentration that you should have.
Mm-hmm. Okay.
So like, I'm trying to think of something equivalent. Yeah, I'm sorry. It's just so it's hard because it's a chemistry thing. So
You could just have like
Just
a
take like
glass of water, and then you're
250
pouring
mil.
it.
What was that, Ian? You had a good
So you can
explanation?
imagine you had a glass of water with NH3 in it, and you pour half of it into another glass, basically, right? So you're gonna have 0.1 moles at the end.
Yeah, that's a good description of it. Yeah. What were you saying, Taylor?
Take 250 milliliters of a 0.4 molar solution. That's basically what you're doing.
That's the right way to think about it. Yeah. Yeah, it's these types of problems like when I read it, it makes sense to me because I've done enough lab work to where I'm just this whole process just I've probably done something similar to it before. Um, but if you haven't done a lot of lab work, it can just seem kind of you can get overwhelming to kind of figure out exactly what the hell's going on because you don't really have something to wrap your imagination around in terms of like I don't know. You've never prepared a buffer, for example, and taken 250 mils out and then added 50 milliliters of acid to it. Everything starts to feel really abstract. So sometimes it helps to draw out like a beaker and sort of diagram exactly what's going on to get a feel for how the volume transfers are happening. Because the volume will totally screw you up at the end, even if you understand what you're doing. Especially when we get to titrations. Titrations will hit this. This is sort of like an introduction. This question is almost like an introduction to titration. So when we work through the titration stuff, it might be a little clearer how to work with volumes because you have to do a lot of that for that. But yeah, that was a reasonably difficult question. All right, 20. This one says the unionized, which reads like unionized, but is in fact unionized. I don't know if maybe that should have a hyphen or something to make it clearer. The unionized form. Oh yeah, we haven't really talked about indicators at all of an acid.
Wait, I'm sorry. Can
Yeah.
I just had one last question about the last one we did.
Oh, I'm sorry. Yeah, I didn't see your question. Go ahead.
It's okay. I just wanted to make sure. But so you realized it was a buffer, and you used the Henderson-Hasselbach equation because after you subtracted out the HCl, there was still like conjugate acid and base left.
That's right. Yeah, that's a good. That's what I was trying to convey. That what I was talking about before. Yeah. Yeah, I knew the situation I was in because for exactly what you're saying. Because after I'm done subtracting the HCl and coming up with these final concentrations here, I still have some base and its conjugate acid. So if I was in the situation where I kept adding HCl and so when I'm at the finish of the reaction, I have HCl, that means that I've consumed all my base and now I'm in a different situation. So I'm not in the buffer situation anymore. So yeah, so what you said is correct.
Okay, thank you.
Yeah. If you want to like in terms of just like thought experiments, you can think about at what point this becomes not true. Like when does this not a buffer anymore? At what HCl concentration? And you can also think about like, what if I added base? Like, at what point does it not become a buffer solution anymore? Those are both good thought experiments to do. Okay. Let's see. The unionized form of an acid indicator is yellow. Is this covered in the LEs at all? Do you guys know?
Up to this point, I had not heard anything about the indicator colors up to this point in LE.
Let's see. I didn't mean it. I feel like that's kind of an unfair question. Were there any other indicator questions, or is that the only one? I don't know if it's worth it for me to go back and give a point to everybody. Let me see if I can do it really easily. I think I can go on the grades page and add a point back.
If
was
you
the only
attempted the
one.
homework, it gave you the right answer after doing it. So if people just attempted it, they could have gotten the right answer.
Okay. All right, good. Yeah, it's not, I mean, it's pretty low stakes anyway in terms of one question on the homework. Like in terms of how it would impact your grade. But all right, let me get back to the damn file.
But yeah, this was the first time we saw anything about an indicator, and this
Okay.
was the only problem that we had on this homework about indicators.
Yeah, so we'll talk about indicators for, I was going to save those for when we got to titrations, but we can talk about them really quick. So indicators are, I feel like, I don't know, maybe school has probably changed dramatically in the last like 20 years since, or 30 years since I've been in elementary school, but I feel like acid-base, like even in an elementary school, you learn a little bit about acid-base chemistry in terms of litmus paper. Or you do that experiment where you take cabbage juice and you see how it changes colors as you change the pH. Those are all indicators. So they're dyes that change color in response to pH. This is saying the unionized form of an acid indicator is yellow and its anion is blue. The Ka of this indicator is 10 to the minus 5. What will be color of the indicator? Okay, so lots of things we haven't reviewed here. In a solution of pH equal to 3. All right. So for the indicator, Ka is 10 to the minus 5. You could write out the indicator. So it's a dye molecule that changes colors in response to pH changes. So if it's Ka is 10 to the minus 5th, that implies that sort of this, like, so the indicator is a big molecule that I don't want to dry out because it's going to make it, let's say, let me indicate it like this. So we're going to call it indicator, IND. And you can think of it as being like an anion, like A minus or something. So that's our indicator. And it has a protonated form that looks like this. And its acid dissociation looks like this. So that's what they're talking about when they talk about the Ka is equal to 10 minus 5th. And so this form is, let's see, the unionized form of the acid indicator is yellow. So this is yellow, and this is blue. So pH indicator is like a pool test or something where you're looking at a color change. This is what they're based off of. It's just the idea that the indicator's like equilibrium constant hovers around, or acid dissociation constant hovers around whatever that pH is. So something that was yellow, let's see. So we need to take this and we need to figure out a way to relate it to the pH is the deal. There's probably a bunch of different ways to do this. One would be able to work out like a Rice table, but I think in general, you can say that like for a particular molecule, let's say, if the pKa is, second pKa, the indicator pK is less than the pH. We could look at the other situation where the indicator pK is greater than the pH. So if the indicator pK is less, let's see. So if the indicator pK is less than the pH, that means that So my dog's barking in the background. It's like just enough to stop my brain from thinking properly. If the pK is less than the pKa, sorry, pH is less, pK is less than the pH. What does that mean? That means that the yeah, so let's see my pKa for the indicator. So our pK is 5. So that means that we're in the second situation. So that means that the pH of 3. So I think you could calculate out the ratio of the indicator by looking at the Henderson-Hasselbach equation. I'm trying to think of like the easiest. What's the most general way to talk about this? I'm doing a terrible job. But you can think of the indicator as being a weak acid, weak base system. And that sort of tells you what the ratio of indicator to protonated indicator or yellow indicator to blue indicator would be, or ionized to unionized, however you want to think about it. So when they're exactly equal, 1-to-1, that's when you'd have a green solution. So if I have a concentration of the indicator that's yellow and a concentration of the indicator that's blue, and those are exactly equal, you're expecting to get a green solution out of this. So that's sort of the intermediate situation. And that's when these two things are equal. And so log is equal to 1. So when the pH equals to pKa, yeah, so I guess the other is that the indicator pH, that's probably the right way to start. So if the indicator pKa is exactly equal to the pH, that means that the pH is equal to the pKa. That means that the ratio of indicator that's ionized to indicator that's not ionized is equal to 1. So 50% of the indicator is dissociated in this situation. So for, say, as the indicator pKa is greater than the pH, that means the indicator is primarily, pKa is 5, so the pH drops. Why is this boggling my mind right now? So if you have, let's say my pK is 10, pH is 2, it's going to be protonated. Yeah, so if the indicator, yeah, so the indicator is primarily ionized in this situation. Yeah, I think I usually think about it in the opposite way. So I'd say like the pH is less than the pKa of the indicator. I think that's why I'm getting confused. Yeah, pH is, all right, so if the pH is greater than the pKa of the indicator, then the indicator is primarily ionized. If the pH is less than the pKa of the indicator, the indicator is primarily unionized.
So when
Yeah,
it's
so
at
go ahead.
equal to 1, why is it green or turn green?
Because you're intermediate, so if the indicator when it's like in its ionized form is blue, and when it's in its unionized form is yellow, when the pH is equal to the pKa, you have 50% of each of those present. Right, so you got a 1-to-1 ratio of the blue to the yellow. And so since yellow and blue mixed together makes green, when they're exactly equal, that's when you have this green solution.
Okay.
And then as you sort of deviate and get more of the yellow or more of the blue, you deviate away from green.
Is that like subtractive coloring then, basically?
So that's subtractive. I don't know enough about color theory to say, but yeah, it's that yellow and blue makes green. Is that subtractive coloring? I have to think about it. Yeah, I guess so you've got a wavelength, so they're both absorbing. So one absorbs yellow and one absorbs green. I forget, man. It's so complicated, like how the retina perceives it. But yellow and blue makes green is basically all I'm thinking of. And like I'm in art class in like 3rd grade, and they tell me that, and I'm like, okay. I'm not thinking about it any more sophisticated than that. Yeah. Yeah. So the pH is less than the pKa. The indicator is primarily unionized. Does that make sense? Yeah. Okay. Good. So the right answer at least. Yeah. So the indicator dissociates completely. It's blue, and if it doesn't, it's yellow. And so at pH of 3, yeah, it doesn't dissociate so much, so it's yellow. That's basically the idea. So for indicators, there's like a whole probably lecture that needs to accompany indicators, but like the idea of an indicator is that you want it's a color changing dye that changes color around the pH that you're interested in. So if you're interested in like measuring a pH around, let's say 5, you want to choose an indicator dye that has a pKa that's around that pH. That's how you kind of the choice of indicator that you use, and it's probably not super clear like why you'd even want to do that, but like when you're doing titrations is where this really comes into play, and so it makes sense to talk about indicators in that context. Yeah, but, we'll talk about that in more detail. Maybe not next class, but on Friday, one of those classes. Probably on Friday. Yeah, we probably don't want to get into indicators until after we talk about titrations. But back before, the indicators are still like in common use, but back before like analytical chemistry technology was really good, these types of chemistry that were dependent on like dye color changes and stuff were just like that's what you used in the lab to kind of figure stuff out. But now we have like fancier stuff like pH electrodes, where you just kind of shove it in a solution. It tells you the pH. So they're not as useful, although still used a lot. Like if you go work in oil and gas and stuff, and you're out in the middle of West Texas, they'll use pH indicators because you don't want to have to take an electrode out there with you. So, but anyway, indicator chemistry is really neat. We probably won't actually be able to get to any of the cool stuff, but almost all dyes, or a large quantity of dyes, are actually acid-base indicators. Like if you ever see, like if you're cooking and you use and you see a color change, a lot of times it's due to pH changes. I'm trying to think of an example when that happens, and I can't, so maybe that's not the best thing. Maybe like food dye or something. Anyway, all right, I'm getting off on a tangent here. That is how that problem works. It was not an easy problem. It wasn't really a very fair problem, so I'm sorry about that. Any other last minute questions? We've got about 5 minutes left. So for any molecule, the utility of this sort of thinking, pH and pKa, is that this isn't just true of indicators, it's true of any molecule. So for example, like what's a good example? Like even let's say you're looking at like let's say you're looking at this. What's the pK of acetic acid? I think it's Ka is it 1.8 times 10 to the negative fifth? So for this, its pK is 4.74. It's a useful like metric as a chemist and for like biochemistry and stuff in organic chemistry. That if your pH, so what this tells me if I know the pKa is that at pHs greater than 4.74, it'll be mostly CH3CO minus, and at pH less than 4.74, it'll be mostly CH3COOH. So it tells you at what point that proton starts to really come off. So if I'm just looking at straight up the pH of a solution and I have a molecule in there and I want to know what form it's in, and you know it's a molecule that has acid-base chemistry associated with it, which most molecules, especially in biology, do. It can exist in one of two forms, right? So it can exist as an acid, or it can exist as its conjugate base. And sometimes you're not interested in the pH as much as you're interested in the molecule itself. So if you're looking at a lot of times, this actually works out to be true. And so if I just know the pH of solution and I know the pK of the acid, so if I know my pKa for this is 4.744, I can say, well, if the pH is 7, let's say, then I don't have to do any kind of real math here. I just say, okay, well, the pH is 7. That's above the pKa of my acid. That means the primary form of this thing is going to be as the base. So once the pH gets above the pKa, I know that the acid that I'm looking at is going to be not protonated anymore. That's sort of what this pH pKa thing is really useful for. And so it's true of indicators, but it's just true of everything.
In the above problem, the pH was 3, but yet the Ka was 10 to the negative fifth, which is smaller than 3. So
yeah, so be careful. So we're comparing the pH to the pKa, not to the Ka.
Oh,
so the pK is 5.
okay.
Yeah. So there, the pH is less than the pKa, so you expect it to be not dissociated. So it's going to be, you know, favor this reactant side. But yeah, this is the thinking, and this actually turns out to be like pretty useful for biology. So like a lot of times, since your body, the like blood pH is, I want to say it's at 7.4. And so that's constant. So you're not like, you know, when you're doing stuff in biology and you're looking at biochemistry, a lot of times you're just stuck at 7.4. So you're not as worried about pH changes like we are in this class. You know, you're not calculating what's the pH of the final solution because your blood is buffered at pH of 7.4. But you are interested in sort of like what the form of the molecule is. So if I've got, for example, acetate or like an amino acid, something present, I can look at the pKa and say, okay, like, you know, like if I have acetic acid floating around in my bloodstream, is it going to be protonated or deprotonated? And I can say, well, I know the pKa of that is 4.74. And since the pH is above that, I know that it's not going to be in the acidic form. It's actually going to look like this. And that's just a really easy way to kind of think about what form the molecule is in at a particular pH, without having to do all this laborious math. So in reality, for most chemists, unless you're doing analytical chemistry or physical chemistry, we don't really like to do a lot of mathematics, even stuff like this where it's just basic algebra. So we have a lot of different shortcuts. It probably doesn't feel that way because I feel like general chemistry is very quantitative. But if you go on to take organic chemistry, you'll see that there's virtually no mathematics in it. Anyway, all right. So that indicator problem is like leading a little bit too much. I think we probably won't get to that until Friday. But we'll do titrations we'll start titrations on Wednesday. And that'll probably, we might do KSP. I might just kick that out until the next exam. But yeah, definitely titrations will be on the exam. So anyway, all right, thanks guys.